What's going on, guys, and welcome back to common mistakes you're making when doing integration by parts. Last time we focused on mixing up U and V, but today we're going to be focusing on another mistake, and that is not focusing on these identities. The reason why this is so important to understand is not because of how often they show up, but rather how rare they are, and by extension how quickly they can derail any question you're working on. And it's exactly because of that rarity that makes people trip up on these types of integrals. Take this question for instance. As you can see, this question is worth 5 marks. However, had I not known the information in this video beforehand, I could have easily gotten stuck, giving me only 1 or 2 marks out of 5. Think about these identities like a blocked nose. It doesn't happen often, but when it does, it makes you reminisce on why you didn't take proactive steps to look after your immune system, and how grateful you will be when it's unclogged, all while you get terrible sleep and can't function properly. This is the same. The explanations of these are quite simple. Why? Because you got them in your exam booklet to start with. So for instance, the first one is 1 over x squared plus a squared is equal to 1 over a arctan x over a. Okay, all you have to do is plug that in. And the other two also have similar, simple, quick fixes. All you have to do is look at what's on the exam booklet and plug it in. Now, just to take a very basic example, we've got 1 over x squared plus 1. Okay, so as we can see, this is going to follow the following format, okay? We're going to have x squared plus a squared is equal to 1 over a arctan x over a, okay? So if we follow that, what do we get? Well, 1 over x squared plus 1 dx, it should technically be dx here, 1 over x squared plus 1 dx is going to equal 1, okay, over 1 arctan x over 1, okay, because if 1 is equal to a squared, therefore 1 is equal to a. Okay, so again, this isn't rocket science, but it's just to illustrate the point here. So therefore what you get is arctan x plus c. Now in this scenario, we've got x squared minus a squared. Okay, so we're going to be applying the identity 1 over x squared minus a squared is equal to 1 over 2a ln x minus a over x plus a. Okay, so in this context, a squared is equal to 16, which means that a is going to give me 4. So therefore here what I get is 1 over 2 times 4 ln x minus 4 x plus 4. Okay, so the answer is going to equal 1 over 8 ln x minus 4 x plus 4 plus c. Alright, now for this one, guys, we're going to be following this identity. So 1 over a squared minus x squared. Okay. The identity here is we're going to get 1 over 2a ln a plus x, a minus x. Okay, again, this is all on the formula sheet. So in this instance, a squared is equal to 25, so therefore a is going to give me 5. Okay, so here, what we've then got is 1 over 10 ln of 5 plus x over 5 minus x. Okay, and that's the final answer for this. So again, this isn't rocket science, but it's just a neat trick to know. Okay? And what's important is, for this one, the absolute value of x must be smaller than a. And for the other one, the value for x must be bigger than a. Okay? Just something to keep in mind. It doesn't really make that big of a difference. But maybe, let's say you had a slightly different example where x was a constant, even though you probably wouldn't do it that way, but then it might be worth considering. But for the most part, you'll be fine. So now, guys, to put this in practice, what I've got here is an example from a paper that I've actually covered on the channel before, but it's a good example to show exactly what we're talking about here. Okay, and for context, this is part B, right? So the first bit was finding these partial fractions. If you don't know how to do that, link in the description. But these are the partial fractions we found regardless. Okay, and it wants us to show that we get ln 54 and pi over 8. So, first off, I can rewrite this because I'm going to say integral between 0 and 2, okay, of 3 over x plus 1. Okay, what was the other one? Minus 2x minus 1 over x plus 4, x squared plus 4. So, 2x minus 1 over x squared plus 4 dx. Brilliant. So now the next bit. The next bit here is, I can say, alright, 0 and 2. 3 over x plus 1 dx. 0 to 2. 2x over x squared plus 4 minus, again, 0 to 2. 1 over x squared plus 4 dx. Now, why have I done this? Why have I done this? Stop the video now and think about it. If you haven't stopped the video, well, here's the answer. What we've done is we've broken this down into two integrals. The first one here can be broken down into ln of x squared plus 4. Okay? And this can also be broken down into something. And we covered that something today. As you can see, this is in the form of 1 over x squared plus a squared. Which means then that a squared is going to equal 4, which means that a equals 2. And so using that logic, what can I say? Well, starting from left to right, we get 3 ln x plus 1. That's going to be between 0 and 2. Plus ln x squared plus 4, which will be between, again, 0 and 2, minus 1 over a, so 1 over 2, make that bigger, 1 over 2, arctan x over a. Okay, so x over 2 between 0 and 2 again. So therefore we get 3 ln 3 plus ln of 8 minus ln 4. Okay, now why have I only got ln 3 here? Because ln 1 is equal to 0, right? Which is why we only get ln 3. And over here we're going to minus half tan x over 2. Sorry, half tan of 1. Okay, and we can plug in 0 as x. This gives us nothing, so we leave that. So this is what we got. So we got ln 27. Okay. Plus ln 2 minus a half of pi over 4. Okay, and applying our ln rules here again, we get ln 54 minus pi over 8. And as you can see, that's what they wanted, and that's what we just proved.